Yeah, thanks very much and welcome also from my side. It's my great privilege today to introduce Pascal Püllmann. Pascal joined my lab in 2017 as one of the really first PhD students, and he was starting on the work to express heterologously the unspecific peroxygenases in yeast. And this was really a start from scratch. We have not done any Golden Gate cloning, which we need for that. We have not done any work with Pichia pastoris or Saccharomyces before. So he really started from the scratch with his entire project. And he's finished his PhD in May and will defend it very soon. And now is a postdoc in my lab for a couple of further months. And now I don't want to steal any more time. And we are really looking forward to your talk, Pascal.
Yeah, thanks a lot for the kind introduction, Martin. And it's my great pleasure to be invited to give a talk today at this great series. And I'm very grateful to the organizers for putting up this very nice series. So today I want to take you on a journey through my PhD thesis. So this one was dealing about with unspecific peroxygenases. So these are secreted heme sialate proteins that are capable of doing oxyfunctionalizations. And in general, they are like always, sorry, just getting to the pointer. So they are named after the fungus they are originating from. And chemically, the mechanism is similar to the peroxide shunt pathway you always also find in P450 enzymes. So hydrogen peroxide is activated by a catalytic glutamate residue, and you form this active compound 1, which then is a very strong oxidant and capable of cleaving this hydrogen from a substrate. You end up with compound 1, and the substrate radical can rebound, releasing the hydroxylated product. So I already mentioned P450 enzymes, and actually they are quite comparable to peroxygenases because of the chemistry they do. So this kind of oxyfunctionalization chemistry is quite comparable. But if you compare the UPOs to the P450s, actually they seem to be quite simple. So they are just relying on hydrogen peroxide, whereas P450 enzymes are in need of like cofactors and also like other domains that shuttle electrons and equivalents to the oxygenase domain. And the chemistry is actually quite comparable. So starting from compound 1, you're capable of doing aliphatic as well as aromatic hydroxylation, as well as epoxidation and heterome atom oxidations. And which is quite unique. You're also able to do halogenation that proceeds via this kind of halogenating species with bromide and chloride. So these enzymes are quite interesting and stated a lot of or caused a lot of bold statement and created a lot of fuss in the community. So it seems to be like the perfect enzyme out there. But so right now you might be wondering why didn't I hear about them before, or why is not already everybody working with that? So when I was starting 4 years ago, roughly, there was just one recombinant UPO described in a standard host, so in Saccharomyces basically. And this was based on great work by the Alcalde lab in Madrid. So they took actually this UPO from Agrocybe. And as you can see in the structure, maybe you get already a clue why it's maybe difficult to produce, because it's heavily glycosylated and you also have disulfide linkage and signal peptide for that guides secretion. So what they did is they introduced 9 mutations to boost secretion from nearly non-existent to up to 8 milligram per liter. And what us really got started was this observation that 4 of the mutations they introduced are within the signal peptide. So our idea was then to build a flexible Golden Gate setup where you can basically shuffle modules together. So we built a panel of 17 different signal peptides that are suitable for secretion of target proteins in yeast. And you can basically just assemble this with different genes in an expression plasmid. So you end up with a UPO expression unit. So first we started with Saccharomyces, but then we also switched to Pichia pastoris, because this is a very interesting yeast also for industrial applications. So there are like some beneficial features when it comes to high yield target protein production and secretion. And with Pichia, it's a methyllotrophic yeast. So this kind of yeast, they have a highly specialized metabolism for methanol, and derived from this metabolism, there are a lot of different interesting promoters, because of course for the cell, it doesn't make sense to produce these gene products if there's no methanol around. So in general, these promoter elements are very tightly regulated and also very strong. So then our idea became to take the signal peptide shuffling approach that I mentioned before, and also combine it with a promoter shuffling for this kind of methanol inducible promoters. And since I'm a great Metallica fan, we named the kit yeast secrete and detect, because that's basically what we do as well. And so we added 11 wood promoters, so 8 of them originally coming from Pichia and 3 from a different methylotrophic yeast. And now basically it's a little bit of an addition to what I described before. So now we have 2 shuffling modules, so 11 promoters and 17 signal peptides. You can shuttle this into the episomal level. So that's basically the level we do also directed evolution on. And if you then have like a nice producing construct or like a nice protein variant out of your evolution, you can just swap it into the integrative level and linearize this and use it for the generation of high yield producing strains without the need for costly antibiotics. So basically, it's very simple. So you just have 50 microliters of your setup. So it's 1 pot, 1 step, golden gate. And you can assemble a signal peptide shuffling library with 17 possible combinations. So that's what we call it first generation, works in both yeast. And then, as I mentioned, we focused a bit on Pichia, and there put this combination together where you can end up with 187 possible combinations in just 50 microliters. And this is the second generation of the system. And now having the library, you can transform it, you can cultivate your yeast, and your protein gets secreted. And then we have the secrete part of the kit already mentioned, but then we get the detect, because basically we also implemented a GFP assay, which can, or with which you can measure the amount of target protein secreted. So this is actually quite handy, because you can correlate your activity to your protein amount. So you just, maybe you would have a variant that is better secreted, so you wouldn't know in the first glance because you just see a higher activity, but so you can directly correlate the activity you see of your variant to the amount. And since we think it's a very helpful system, at least in our hand, working pretty nicely, we put it on EdgeGene so that the community can use it also, of course, for other target proteins. Of course, now I got a lot of work on the system, but of course, we also wanted to look into UPOs. So we choose a lot of new UPOs, and we got very lucky with our choosing. So we were able to produce a lot of novel UPOs for the first time, and also some firstly in yeast. And as you can see, some are clustering quite closely, so they're quite homolog. But they are also, for example, if you look at the DCA or TTE or CGL UPO, they are totally different clades. So the homology is actually not that high. So we got also quite a high diversity there. And so, of course, now we get the constructs, we got the enzymes, but we also, with this kind of shuffling, our idea was, of course, that we also get like very powerful strains for protein secretion. So we check that, so like on an integrative level. And I have to say, we actually didn't optimize that. So it was always standardized. And now what I'm going to show you 4 examples, which I found quite striking. And it's always milligram per liter of target enzymes. So the first thing we tested was CGL UPO. So this one was not reported to be not producible in prokaryotic systems. And actually we were like able to produce a bit in Saccharomyces, not too much, but already with transferring it to Pichia pastoris, we could already get up to 9 milligram per liter. So very good yield to work with. TTE UPO was a different case. So actually here we had like a very high production titer already in Saccharomyces. And then we lost a bit when we got to Pichia pastoris, to the signal peptide shuffling, but then recovered that when we also implemented the simultaneous promoter shuffling. So here we are nearly to close to 25 milligrams per liter in shake flasks. And another thing was that actually, like lately, there have been some first reports on production of UPOs in E. coli, which I already mentioned can be quite challenging because of glycosylation as well as disulfide linkage. But actually there were some reports, and one of those included the DCA UPO. So they reported roughly 2.6 milligram per liter. And we took this UPO and put it to our shuffling system, and we got really lucky. So this seems to be also very suitable for a production in Picha, as we can get up to 60 milligram per liter. Using UPOs as a test set was already quite good because they are challenging enzymes. So we already felt pretty confident about the system, but we also wanted to show that it's also working with other enzymes because of course there are other very interesting enzymes to work with. So we took lactases, which are also of great interest, and took a lactase that was actually reported to be producible with Picha, and original reports stated 10 milligram per liter. And by applying our combined shuffling, we could triple that, going up to 30 milligram per liter. So, and looking at the promoter distribution, so we took like the 80 top hits, we could see that there was actually clear preference for some promoters, so this FLD1 and FND promoters. And there was a clear tendency that these promoters that have occurring de-repression, which means that they're already getting active when the first carbon source becomes depleted, which is in our case glycerol, that this kind of smooth transition promoters, I would call them, are very powerful in our setup, because this classical, maybe you recognize this, AOX1 is a very classical on-off promoter, so non-active when there's some other carbon source around and becomes active as soon as methanol is around. They are actually not so good in our hands, at least in this episomal system. Looking at the signal peptides, this was a more broad distribution. So actually average occurrence would be roughly 6%. And as you can see, a lot of our
Yeah, I think we lost him.
I got disconnected, it seems.
Looks like you're back.
Yeah, welcome back.
Yes. Sorry about that.
No worries. This is what happens in virtual talks, right?
Yes,
there are technical difficulties.
The German digitalization, we're very bad with that, I guess.
Okay, looks like your slides are back up. Take it away.
Sorry about that. I'm gonna go on. So now we got a lot of molecular biology and a lot of production, and now we wanted, of course, to use the chemistry, because as I mentioned, they are very interesting. Geez. Guess no. Yeah, it's working again. Sorry. So we wanted to do also, of course, exciting chemistry with this kind of catalyst. So, for example, we took this compound, which is a phenylethylamine, and we wanted to introduce this kind of stereoselective hydroxylation, because if you go from this compound, so this amino alcohol, basically, you end up with a lot of interesting biogenic compounds, so like adrenaline, but also with a lot of drug candidates. So it's a very promising scaffold. And our idea was then to introduce a hydroxyl function with the enzyme, and then to be able to do classical chemistry on the amine. And actually there, we could have a really nice example why it makes a lot of sense to broaden the enzyme panel, because when using the classical enzymes that have been reported before, so AA-UPO and MRO-UPO, we couldn't see this kind of transformation. But using then our novel enzymes that we have been discovering before, we could already get quite decent turnover numbers, so roughly around 1000 without optimizing, and also very high EE for the S alcohol. Having that, we could also then go to a proof of principle hydroxylation on a preparative scale. So we are really like in a good range to do some chemoenzymatic workflows there. And another work that has been done by my colleague Anja was to take one of the new enzymes, which was the MTH UPO, and target 9 amino acid residues within the active site for single site saturation mutagenesis, and also to do recombination afterwards. And screening these libraries by using this kind of surrogate substrate, which eventually then leads to a strong absorbing compound. So it's, of course, very easy to screen on a plate reader. And by applying directed evolution there, she got like really lucky. So already with not so much effort, actually, we could get to a 16-fold improvement in catalytic efficiency. And which was even more interesting then is that when using this kind of evolved variants that were very active on the scaffold, but using differently substituted naphthalene derivatives, she could, for example, in this case, while using this 2-methyl naphthalene, she could get chemodivergent synthesis. So like depending on the enzyme, she could actually achieve 3 different products, sorry. One of them being vitamin K3. So it's a very interesting starting point. To sum it up, I hope I could convince you that we were able to build a high throughput secretion and evolution system in two-yeast. And we shared this system with all of you through AdGene. And of course, using the system, we achieved our goal to enlarge, or like our primary goal, to enlarge the pool of recombinant UPOs. So back in 2017, I mentioned that 1, and now we are actually having 14 reported. So 7 of us, and also like a lot of other groups are starting to work on UPOs. So there have been also other UPOs reported there. Then I just mentioned that we were able to show or report the first directed evolution campaign of a Y-type UPO by screening 4,300 clones. And we could show stereoselective UPO-catalysis on a preparative scale. And as I mentioned, this is like a very nice starting point to implement this reactivity into chemoenzymatic workflows. And yeah, primarily what I talked a lot about was how to optimize your expression yields. So we could actually, for 8 enzymes, so 6 UPOs, but as well as a lipase and a lacase, we could optimize the yields through this kind of combinatorial shuffling system. So finishing up with a little bit of a perspective there. So something that I would consider the holy grail right now is to do target-oriented UPO engineering in a high throughput format. So aside from the work I already presented, we did some other work lately. And so one of that was to develop Golden Gate-based high throughput mutagenesis technique. And yeah, I talked a lot about this kind of high throughput productions. And then my colleague Anja, which is like very brilliant when it comes to analytics as well, she developed actually over the last couple of years some very sophisticated GCM methods. So basically, this is an example which I guess is like the prime example. So she took 3 aliphatic substrates, and just like in one pot, she's able to detect 6 different products that are of high interest. And this is like also performed in 96 well plates. So I guess this connecting the dots of these 3 systems, we can get to like very, very interesting directed evolution campaigns in the future. With that, I'm at the end, and I want to thank the group, especially Martin and Anja, for all the great support and mentorship over the last couple of years, but also all the past and current members of the group. And yeah, all the collaborators at the Institute, external collaborators, and especially also the Landesgraduiertenförderung for funding my PhD. So thanks for the attention, and I'm very happy to answer questions.
Well, great talk. Thank you very much. Great results. I know that there's a lot of work to get this expressed. You showed there a slide where you investigated the hydroxylation in benzylic positions, and there were various targets. You had adrenaline and others on that, which are, well, I was wondering, do you have any indications that these phenolic groups would not mess up your reaction? Because this is now, well, high reactive, I would guess. Did you test any of those, especially? I mean,
it's a good point. Yeah, actually, we are like about to test that. So we, as I mentioned, we got this proof of concept on the scaffold, and of course now we're looking into into like targets, so like substitution patterns. But yeah, we haven't tested that, but we are hopeful that we can achieve, because at least so like the orientation seems to be pretty good, and the stereoselectivity as well, reduced selectivity. But yeah, we can't say for certain. It's more like a future approach then, or like something we're currently looking into.
Would you use protecting groups there? Otherwise?
Yeah, I mean, we got this phthalimide protection on the amine.
Okay. Oh yeah, yes. On the phenolics.
No, not yet. As I mentioned, we are like currently underway.
Okay.
We just had this kind of proof of concept there.
Okay. Okay. Good luck. Thank you.
Yes. Thanks.
So Pascal, great talk. I have another question regarding heme incorporation, because that's a pretty important thing for UPOs and other heme-dependent enzymes. So your titers were impressive. Can you comment on whether your strain was able to keep up with that protein production, and did you get like one-to-one heme incorporation?
Yeah, actually, I mean, I can say a bit about that. So basically, when we do it in microtiter plates, so like, of course, or like normal setup, I would say, daily life setup, then we supplement a bit of hemoglobin. This seems to be beneficial, but actually when we go to shake flasks, we actually don't supplement at all. So it really is this kind of 25 milligrams per liter we get. They are also like fully loaded. So we didn't see any effects that we had like some missing incorporation or like some effects there. But I mean, we didn't go to fermenter yet. But in shake flask seems to be we also had different enzymes roughly around 25 milligrams right now, and they seem to be working quite fine. So we don't supplement anything in shake flasks.
Yeah, that's great to hear, because one of the challenges we face in pharma industry is that a hemoglobin or heme mainly comes from blood, and our enzymes need to be free of components from animal origin.
Yeah.
So that is actually a tricky problem for us to solve. So great to hear that your strains are so efficient at heme incorporation.
It's actually the Y-type strain, so it's not a special strain. Mm-hmm. It's just the standard picher you get like on every corner.
Mm-hmm. Excellent, thank you.
Maybe I could just ask one on you, if that's okay. So first of all, great talk, Pascal. I really enjoyed that.
Thanks.
Just is in terms of the tolerance to hydrogen peroxide, what kind of concentrations of peroxide are tolerated, and what are the structural features that make these enzymes more tolerant to peroxide versus a P450, for example? Is it known, or?
I mean, it's I mentioned some pitfalls of the enzyme. It's actually the one I missed out on. There has been also a lot of work on doing this kind of in situ hydrogen peroxide supply. I guess it's like hard to generalize. So, I mean, as a rule of thumb, I guess like most of the literature and also how we do it is that 1 millimolar is maybe a little bit of a threshold there. But I mean, it also depends on the enzyme. So we got a lot of different enzymes now, which we didn't characterize like all on them for the like their tolerance. But also depends on the reactions. But actually, I don't know about P450. Maybe you can tell me something about tolerance there. But I mean, we didn't have so big problems. But of course, we also don't use like high millimolar hydrogen peroxide. But this is like I guess also like occurring with a lot of peroxidases. So it's like, unfortunately, like a really common problem that are quite intolerant to higher concentrations, that you get this kind of heme bleaching and destruction of crucial residues. So yeah, that's a drawback. So of course.
Okay, thanks, cheers.